Hi students, and in this video we're going to cover section 4.3 and 4.4. I'm going to go over some different functions that we haven't seen. So far I believe we've seen linear equations, and we've seen quadratic functions, which were the parabolas. We're going to talk about some more common types of functions, and then I put it in the same video 4.4, the transformation of those functions, which basically means the shifting or stretching or flipping of those functions. So the first type of function we're going to talk about is the function of the form ax to the n. So far we've seen things where we have x squared. So here's where we can actually have higher powers of x. If the n is a negative number, it's going to look like one of these graphs. So obviously, if n is 1, we've got a linear equation. It's going to be a straight line. But if n is a 3, 5, 7, 9, etc., then what we're going to have is this kind of cubic function where it's almost like half our parabola. It's almost like a parabola, but instead of the positive and negative side mirroring, the negative sign actually gets to be negative. And that's because we are an odd exponent. And so that odd exponent allows for negative values of x to result in negative values of y. Okay. So those are anytime x is to an odd power. And really, as the power of x just gets higher and higher, we keep the same shape, but it just gets more extreme. I don't know if you noticed, but the corners here are tighter. Okay, so before, when x is less than 1, it's very, very small. And as soon as x gets greater than 1, it really blows up faster for higher powers of x. In this case, when our n, our exponent, is a odd number, the domain and the range of our function are both going to be all real numbers. Okay, we can plug in anything we want and we will get out every possible value. Okay, this is going to be true for higher powers as long as the exponents are odd. Now, if our exponents are even, we have our parabola situation. Because the even exponent causes our inputs, whether our input is negative or it is positive, since it gets raised to an even power, it gets spit out as a positive no matter what. So that causes us to be symmetrical around the vertical line, and the left and right sides look the same. The same kind of situation happens where higher powers of x just get more extreme. Okay, when they're smaller than 1, they're very, very small, and as soon as they get bigger than 1, they blow up very fast. So just more extreme growth, the higher power of x that you have. In this case, our domain is all the real numbers. We can plug in anything we want, but it is only going to spit out 0 or positive numbers, right? You can never square or cube or bring to the 6th power any number that will give you a negative number. So the next type are going to be functions of the form a over x to the n. Notice that this is basically equivalent to where our n, or where our exponent, is a negative number. Okay, so here we have basically negative powers, or we can say we're dividing by x instead of multiplying by x. The domain in these is going to be everything besides 0. Notice you can never plug in a 0 because that makes our denominator 0, and that makes our function undefined. Okay, so our domain is negative infinity to 0, not including 0, and 0 to infinity, right? But the range depends on whether or not our exponent is even or odd. If our exponent is odd, just like before, then we can spit out negative numbers for negative inputs, right? But if our exponent is even, then it makes everything become positive, right? Just like when you square stuff, the only thing you can get out is a positive number. So then that's kind of cuts our range in half. So when n is odd, our range is negative infinity to infinity, excluding 0. And when n is even, our range is 0 to infinity, also excluding 0. If you want to take a look at the shape of these graphs, you can notice that we have a vertical asymptote right around where x is 0. So this vertical asymptote is because when x gets really, really close to 0, we have a tiny denominator and a fixed numerator. So this fraction becomes a really big number, either big positive or big negative. But then once x becomes 0, it's undefined, okay? And so that's how we jump across the axis like that. Right. So again, if our exponent is odd, our domain and range is everything but 0, 0. And if our exponent is even, our domain is everything but 0, and our range is all positives, okay? And this is for the case where we can call this a over x to the n, or you can say this is a times x to the negative n, okay? All right, let's talk about a third kind of function. So now we're going to talk about fractional exponents of our variable, okay? So a fractional exponent, recall, is the same thing as a radical number, okay? Or a root or square root or a cube root or a fifth root, okay? So in this case, the domain and the range are going to be the entire set of real numbers when the index is odd, okay? And when the index is even, the domain and the range are only going to allow for positive numbers, okay? That's because you can't take the square root of a negative number, so we are not allowed to plug in negative numbers, and if we can't plug in negative numbers, we won't get out negative numbers, okay? These essentially, these follow the same rule as before, where as our powers or our index gets larger, by index, I mean the denominator of the exponent. The denominator of the exponent is the same as the index of our radical, depending on how you want to represent your function. Oops. Okay, as that index gets larger, our function just grows more tightly. Okay. All right, and again, if the exponent is even, then it cuts our domain and range in half. Finally, functions of the form a times the absolute value of x. Here, our domain is all real numbers, but our range is from 0 to infinity when a is positive, and that's negative infinity to 0 when a is negative, okay? So basically, this is very much like a parabola, except instead of growing at that different rate, it's essentially two linear equations. Now I'm going to move into section 4.4, where we talk about how we're going to shift all of these equations. So let's go straight from that absolute value function. Just like the way we shifted our quadratic functions, we are going to shift all of the functions you have just seen. We have the coefficient a out in front that is going to determine whether we open up or down and how fast we open. And then h and k are going to be our h is the horizontal shift and k being the vertical shift. Keep in mind, this general form has a negative sign here. So if you have x plus something, really that's x minus negative something. Okay. So let's take a look at how some of these shifts look by plugging in some points. If we have our function is equal to the absolute value of x plus 1, well, that plus 1 is going to increase all of our y values. So we'll in a couple x values, and we see that our y values, our outputs, are just one higher than they are for the function absolute value of x. So we've shifted our function, just everything has shifted up by 1 because of this +1. Now, if we added 2 inside of the absolute value bars, just like when we did it inside parentheses in our quadratic functions, this is like subtracting a -2. So our h is -2, which means we're going to shift 2 to the left. Then this 3 is going to cause us to grow 3 times as quickly. So if we plug in some points, you see that the base of our absolute value is when x is -2, because we've shifted 2 to the left. All right, and we grow 3 times as fast as we did before. In this third example, we've got a x -1 inside of our absolute value bars. So our h is a +1, saying we're going to shift to the right by 1. And then we subtract 3 at the end, meaning we're going to shift up by 3. So we're going to shift to the right by 1 and, down by 3. So we're going to go over and down. So indeed, instead of being at 0, 0, we go to the right by 1 and down by 3. Okay, so that's how these shifts work actually for all these different functions. Let's take a look. Really do be careful that x minus h is critical. If you see an expression with an x plus h, you need to think of it as an x minus -h. So we'll do our quadratics, which we, our a times x to the n. And here we are now going to expand it to allow for the shifts in the x direction and shifts in the y direction, as well as stretches according to a. So our first equation, f of x is x squared plus 1. Well, that +1 comes after we square the x, so it is just going to shift everything up by 1. And you notice that the vertex of our parabola is shifted up by 1, so it's at 0, 1. Now in our second equation, x plus 2 to the 5th power. So we're to an odd power, so that means we are going to not be a parabola, but be kind of that S shape. This allows for negative numbers. And we've got a +2 inside the parentheses, so that's really an x minus -2. What that means is that's going to shift us to the left by 2, and we don't have any shifts in the y. So here is our basic shape, and instead of at 0, 0, we are at x is -2, y is 0. Okay, shifted everything to the left by 2 because of this. All right, in our third example, our function of x is -3 times x minus 1 to the 4th power plus 2. So we've got all 3 pieces here. The -3 is our a, and that's going to make us be open upside down, and it's going to multiply our outputs by 3. So it's going to be 3 times as steep. This is x minus a +1, so we're going to shift to the right by 1, plus 2, so we're going to shift up by 2. All right. So we'll see that this is a 4th degree. So it kind of looks like a parabola, but it opens more extremely. It's opening down, and its vertex is at 1, 2. So here's our origin. We move right to the 1, up by 2 is our vertex. And when we step 1 to the left and 1 to the right, we decrease by 3 because of that -3. Okay, so the shifting basically works the same for all of these different functions. You just have to kind of get used to doing it. Right. So now let's talk about shifting function of the form a over x to the n. Okay. Now here, just remember that your fractions can look different. This could be a times x to the -n. It could also be written like that algebraically. So we have our a already, and now we're going to introduce that h and that k if we want to shift stuff around. So our first example, f of x equals 3 over x to the 5th plus 1. So a is 3, h is 0, and k. That means we are going to be shifted up by 1, and then everything is going to get 3 times steeper. Right. So you see kind of the center of our graph is shifted up by 1. Okay, and it's hard to see this 3 times steeper, especially when we've got an x to the 5th, but basically you could just plot a couple points to kind of see how that opens up. In our second example, we've got 1 over x minus 2 all to the 4th power. So that x minus 2 means that our h is a positive 2, and that's going to shift us to the right by 2. Right. So notice our origin is here. We've shifted to the right by 2, and that's where the center of our graph now is. This dot, by the way, is not a part of the graph. It's just me kind of pointing out where our points of symmetry are. So in this graph, we've got a line of symmetry here at at x equals 2. And this graph, we've got a point of symmetry. It's symmetrical about the point 0, 1. Our third example, -5 over x to the 3rd minus 2. So here our a is -5 and our k is -2. That means we're going to be flipped, made 5 times as steep, and pushed down by 2. Okay. So you can see the center of our graph is at 0, -2, because everything's been shifted down by 2. Oops. All right. And unlike our other graphs where if our inputs are negative, our outputs are negative, and inputs positive, outputs positive, we're switched because of this negative sign out in front. All right, let's talk about shifting functions of the form ax to the 1 over n. And remember, these are basically our radical functions. Same thing. If we do something to the x first, it's going to shift us in the x direction. If we do it at the very end, it's going to shift us in the y direction. So in our first example, we've got the cube root of x minus 2, and then from that, we're subtracting a 4. So our h, a 2, and our k is a -4. This is a cube root, so its domain is all real numbers. So it's going to go off to the left and to the right infinitely, and its point of inflection is going to be at x is 2, y is -4. For our second example, -2 times the 6th root of x plus 1. Here we've got a 6th root. So since it's even, our domain is only positive numbers. We're going to be upside down though because of that negative sign, and we're going to open twice as fast. This plus 1 is going to shift us up by 1. Okay, so our kind of origin here, so when x is 0, y is -1, or sorry, y is +1. That's what shifted us up by 1. It's right here. And then we open upside down because of that negative sign. And our domain does not include, our domain is only 0 and larger, and our range is from -infinity to 1. For our last guy, notice that our a is 1/4, so we're opening really flat. We are a 5th power, which is odd, so we open in both directions, and this x minus 1, that -1, shifts us to the right by 1. Now let's talk about piecewise defined functions. So a piecewise function is going to have 2 or more formulas, and each is going to describe a certain part of the domain. Okay. So let's just do an example. If our function is -2x minus 2 for x less than or equal to -1, and our function is x squared is greater than -1, let's try to sketch that graph. So notice that when x is between -infinity and -1, including -1, we have that linear function. So we want to just graph that linear function, but only for x's up to -1. And then we're going to be quadratic from -1 to infinity, but we don't actually want to include the exact point at x is -1. So from -infinity up to x is -1 in this whole range, or sorry, in this domain here, we are at that linear function. And then as soon as we switch over from less than or equal to -1 at this line, we switch to our quadratic, and everything on this side of the line, x equals 1, we are in our quadratic. Now, notice that we use a closed circle at the point -1, 0 to indicate we are including that value in our graph, because indeed, when we are at x is -1, we are evaluating the linear function. Then we use the open circle for our parabola, because we're not actually evaluating the parabola at x is -1. We are only evaluating the parabola when x is greater than -1, but we get kind of infinitely close to that point. Okay. So remember how to use your open and closed circles. All right, that is everything from 4.3 and 4.4. Good luck on your homework.